Preferential number you have to give. I've already told you the horizontal bonds are projecting towards the viewer. If you are a viewer here, then this compound is a Fischer projection to you, not to the one who is standing at the back of the blackboard. The horizontal bonds are always projecting towards the viewer, whereas the vertical bonds are away from the viewer. Now I'm going to number the preferential order to the various groups attached to the asymmetric carbon center. So this is the asymmetric carbon. See here carbon is attached. Here also carbon is attached. Here oxygen is attached. Here hydrogen is attached. When you look at the atomic numbers of these elements, oxygen is with the highest atomic number, so it is given the number 1. The first preference is given to this. When you compare these two carbons, both are with the same atomic number. Therefore, we look into the other atom which is attached to this carbon, the other atom which is attached to this carbon. So then when you compare the next atom, here it is hydrogen, here it is oxygen. Oxygen atomic number is higher. Therefore, this is given the second preference. And then this is given the third preference. And then the hydrogen is given the fourth preference. Now my idea is to bring the hydrogen, which is given the least preference, to the back position. I want to bring this hydrogen to this position. What should I do? I have to turn the molecule like this. So I am turning. While turning, what will happen? Look here, I am simply turning the molecule. I am turning carbon, right? This becomes a solid bond. And here the hydrogen has come. And this becomes a solid bond where methyl group has come. Whereas this becomes dotted, which means this is away from the viewers. And then this becomes COOH. See, simply I rotated. But this formula is not a Fischer. This is not a Fischer. Why this is not a Fischer? Only the horizontal arms should be projecting towards the viewer, not the vertical one. But in this case, the vertical is projecting towards the viewer. I want to change this. What I can do, I can rotate the molecule like this. When I rotate the molecule like this, what will happen? These two bonds are away from the viewer. They will come back, right? So the new configuration, what I will be getting is, see, the OH will go to this side, but it will be projecting towards the viewer. COOH will come this side. It will be projecting towards the viewer. Whereas these two bonds will go away from the viewer, but CH3 will remain in its place and the H will remain in its place. Right? See, one rotation like this, another rotation like this. Now, according to our preference, 1, 2, 3, 4. So 4 has brought down, which means that this is away. Now, you put an arrow mark according to the increasing order. 1, 2, 3. Don't get confused, sir. In between, I am crossing the 4. No, that is not your idea. You forget this. You are only comparing these 3. That is why the least preference has brought to the back. Right? So 1, 2, 3. So the rotation is anti-clockwise. So this is yes configuration. This is yes configuration. Any doubt? If anybody has any doubt, you can ask me. I think now it is clear for you. Now, when I do it for tartaric acid, you can easily understand. Let me do it for tartaric acid, because tartaric acid is with two asymmetric centers. First, I take, there is OH, OH, H, H, COOH, COOH. Let's remember, this is asymmetric carbon 1, asymmetric carbon 2. Now what you have to do, so these two bonds are projecting towards the viewer, these bonds are away from the viewer. You can consider this entire unit as a group. In order to find out the configuration of the asymmetric carbon 1, you can treat this entire group, this carbon with along with its three groups, everything as a single group. So I can rewrite this structure like this. So carbon is here, OH is here, H is here, another COOH is here. Here, this entire carbon is a group where carbon connected to oxygen and all that. Now I want to give a preferential number. So oxygen is given the first preference. Here carbon, but this carbon connected to a O by double bond and another O by a single bond. Therefore, it can be considered as it is connected to 3 oxygen atoms. So this is given the second preference. This carbon is connected to 1 oxygen and 1 more carbon and 1 more hydrogen. Therefore, this is given the third preference. So this gets 3, this gets 1, this gets 2, and this gets 4. So my idea is to bring this hydrogen down. I turn the molecule like this. So what I am getting is a carbon. Hydrogen has come down, but it is projecting towards the viewer. So what has gone up is oxygen. So the third preferential group has come here. Let it be anything. And this is COOH. So this is 1, 2, 3. Now this is not the Fischer because the horizontal arms should be projecting towards the viewer. So I turn the molecule like this. So what happens? Only the third group and the second, they get interchanged and the molecule becomes a Fischer projection. So the third carbon has come here, COOH has gone there, but OH and H, they remain in the same place, but only thing is they are away from the viewer. So now this is the first preference, this is the fourth preference. So now when I put an arrow mark in the increasing order of the preferences, 1, 2, 3, this is R configuration. But this R configuration is for the first asymmetric carbon, so it is given 1R. 1R. Now, for the same molecule, you can write, here it is OH, here it is COOH, here it is H. This entire unit can be considered as a separate group. So similarly, this is given 1, this is given second preference, this is given third, this is 4. This is for the second chiral center. Now, as usual, my idea is to bring this 4 here, so I turn the molecule like this. So what happens? Carbon is here, hydrogen has brought down, so OH has gone up, and as I turned like this group has come, and here it is COOH, but this is not a Fischer because the horizontal arms should be projecting towards the viewer. So I turn the molecule like this. When I turn like this, what happens? COOH and the group with the third preference, they get interchanged. So now the molecule becomes a Fischer. Here it is third preferenced group. Here it is COOH, which is second. Here the OH, which is the first preference. Here it is the hydrogen with the least preference. So what happens? When you go according to the increasing order of the preferences, it is yes. So 2 yes. So this tartaric acid is with the configuration 1R 2S. 1R 2S. Are you able to understand now? 1R 2S. Now let me try for the mirror image of the same tartaric acid. Let me see what I'm getting. So I just rub all the unnecessary things. So we can confirm that this is 1R2S configuration. So this is the configuration of this tartaric acid. Let me see what is the configuration of its mirror image. I'm going to take the mirror image of this compound. So what is the mirror image? Here it is OH, here it is H, here it is OH, here it is H, here COOH, COOH. Now this is carbon 1, carbon 2. So similar procedure, I treat this entire group as a single substituent. So for the first carbon, so here it is H, here it is OH, here it is COOH, here it is the other carbon substituent. I can give a preferential number 1, 2, 3, 4, but at this time, this hydrogen has to be brought here. So I turn the molecule. What I am getting is C. Hydrogen is brought down. So this OH goes up. Okay. Now, as it is brought down, this will come here, COH. This is third preference. But this is not the Fischer. So one horizontal rotation is also to be performed to get to the Fischer projection. When I do it horizontally, I am getting COOH here, another carbon here, OH there, hydrogen here. So preferential order 1, 2, 3, 4. So the least preference has been brought down. So when you put an arrow mark in the increasing order of preferences, it is in the anti-clockwise direction. So this is 1s configuration. 1s. Similarly, when you try for the second carbon, so carbon, hydrogen, oxygen, above it is the another chiral carbon group. Here it is COOH. So this is 1, 2, 3, 4. Now this has to be brought here. So I rotate carbon. Hydrogen has come here. So OH has gone there. And then this group has come here. And then this COOH has come here. But this is not a Fischer because horizontal arms are away from the viewer. So one horizontal rotation has to be done. When you do the horizontal rotation, what you are getting is the Fischer projection, the group with the third preference on your left, and COOH has come to the right, and here it is OH, here it is H. So preferential number 1, 2, 3, 4. So when you do it, when you put an arrow mark in the increasing order of group preferences, it is 2R. Now look here, this tartaric acid is 1R2S. This tartaric acid is 1S2R. 1S2R. So the mirror image and the original compound, the enantiomers, they have the opposite configurations. 1R2S, 1S2R. And one more thing you should understand here, the two asymmetric carbons, when one carbon is with R configuration and the other carbon is with S configuration, both this is with R. R means it is this side. S means this is this side. Here it is S and this is R. That is why they are optically inactive due to internal compensation. But this direction is not the direction in which the plane of the plane polarized light is turned. But this is preferential, group of preferential order. But it can be interpreted as the optical inactivity of the mesotartaric compound may be due to this. Now, when you do the same for the enantiomers, let me try. I suppose you might have understand by now. Let me try it for the other type of tartaric acid. OH, H, OH, H, COH, COOH. Let me do it for this and its mirror image. See, its mirror image, OH, H, here H, it is OH, COOH, COOH. So this is a chiral carbon 1, chiral carbon 2, chiral carbon 1, chiral carbon 2. When you take this, let me think of the first one, first chiral carbon. Here it is OH, here it is H, COOH. The entire chiral carbon is taken as a group. Preferential order 1, 2, 3, 4. So this has to be brought here. So I'm bringing it down, but it is not Fischer. So OH goes up, whereas OH goes up, COOH comes here, and then the third group goes over there. So in order to make it a Fischer, a horizontal rotation has to be performed. So what happens? The third group comes here. Okay, COOH goes there. So hydrogen here, OH there. So the group with the least preference has brought down. So arrow mark in the increasing order, this is 1R. So this compound is 1R. Let me do it for the second carbon. COOH, H, OH, the group. So see, these two are two different groups. Okay. Now, this is projecting towards the weaver. They are away. Preferential order 1, 2, 3, 4. This hydrogen has to be brought here. So I simply rotate the molecule in the plane of the blackboard. What I'm getting is hydrogen has come down. So OH has gone up. So when it comes here, COOH goes there. And then the third group comes here. This is not a Fischer projection. So one horizontal rotation has to be performed. When you do it horizontally, we are getting the Fischer with the third preferenced group here and the COOH here. Then here it is H, here it is OH. Now this is a Fischer. So the order of preference 1, 2, 3, 4. When you put the arrow mark, this also becomes R. So this is 1R, 2R. 1R, 2R. Is that right? Now, you try to find out the RS configuration for the mirror image compound. Do it yourself. You do it yourself and come with the answer. Do it yourself. Let me disconnect the meeting now and rejoin, and then you come with the answer.